In this presentation, we're going to look at R as flip-flops and see how level and edge triggering are achieved. Recall that a flip-flop is the elementary unit of memory. It holds a single bit of information, a 1 or a 0, a high or a low. There are two requirements. The circuit must be able to hold a state. So it should, if it was given a 1, stay a 1. And if it was a 0, stay a 0. So it must be able to hold. And it also must be able to be changed, to set or reset, to force it to be a 1 or to force it to be a 0. Then it will then hold. There are basically two categories of memory, SRAM and DRAM, static RAM and dynamic RAM, and these types of memory differ in the way in which they hold the state. In DRAM, dynamic random access memory, the state, the 1 or the 0, the high or the low, is held as a charge on a capacitor. So the capacitor is either charged or it is not charged. But charges tend to leak off a capacitor, and that's why dynamic RAM is dynamic. So there's the state, the charge is leaving, and then it will need to be periodically refreshed. In SRAM, static random access memory, the history dependence, the remembering, the holding is achieved by a feedback mechanism. Feedback is when the output or some part of the output comes back in as input. And so that is how SRAM is going to do its holding through a feedback mechanism. And that means it's not going to require any refreshing. That's going to be part of the reason it will be faster, but it's also going to be a more complicated circuit. So it's going to be more expensive and take up more space on a chip. And so it's usually reserved for special cases like caching or when we really need high speed. Another example of feedback is sort of when you have a microphone and a speaker. So someone is speaking into a microphone, and then that voice is being amplified and put out in a speaker. But if the microphone picks up which is an input device, picks up some of the output of the speaker, then that will be a feedback loop, and that's that sort of crazy screeching you hear sometimes with sound systems. In the diagram shown here, we have an RS flip-flop. It has two inputs labeled S and R for setting and resetting. And there are two outputs, Q and Q prime. So one of the outputs is sort of considered to be the primary one, that is the Q. That's sort of an arbitrary choice. And then the other one, as suggested by the name, is supposed to have the opposite state, so that's why it's called Q prime. Then the logic part consists of two OR gates and two NOT gates, and then we see that on the wire coming out of the upper OR gate that leads to the Q output, we see a junction, and that is coming back around, going through an inverter, going through a NOT gate, and then coming into one of the inputs of the lower OR gate associated with the Q prime. And then also the Q prime output also has a junction that is fed around and again inverted, put through a NOT gate, and then is one of the inputs to the OR gate in the upper portion along with the S input that gives the Q output. So that wire coming back from being an output and coming back around and feeding into the OR gate. So it's both sort of the output of an OR gate and the input to a related OR gate. And so this is feedback. So here we are looking at the help from Electronic Workbench, a sort of previous version of Multisim on an RS flip-flop, 74279. And we see that when S and R are both low, that's labeled as the no change. When S is low and R is 1, that is going to be our reset, and we're forcing the primary output Q to be a 0, and therefore Q prime are here written as Q bar as a 1. When S is 1 and R is 0, we're making Q 1, we are setting, and Q bar or Q prime will be the opposite. And when S is 1 and R is 1, they say undefined, and I'm going to call it the undesired state, that Q and Q prime are supposed to be opposites, and they will not be opposites in this case. So the Q output is inverted and fed back as an input. Similarly, the Q prime output is inverted and fed back in as an input, and the Q and Q prime, as the name suggests, are supposed to be opposites or inverses of one another. Let's look at the hold operation, which is when S is 0 and R is 0. So we want to see that this holds our state. So we have to imagine that we were in a state that is worth holding, and what we care about is that Q and Q prime are opposite. So let's imagine that the Q was a 1 and the Q prime was a 0. So let's look at the Q prime, which was 0. Then we're going to invert it. As we're doing the feedback, we invert Q prime. So Q prime was 0, so now not Q prime is a 1. That 1 gets ORed with the S, which is a 0 for the hold state. And so we take the 1 and the not Q prime, which is a 1, and the 0, which is an S, and we OR them. So the output of that upper OR gate is a 1, and so we're just keeping that state, that Q. Now let's look at that 1, that Q was a 1, and it gets fed back and inverted. So Q was a 1, so not Q then is a 0. That gets ORed with the R, and the R is a 0, and the not Q is a 0, so 0 or 0 is 0, and that's keeping the Q prime output as 0. So we started off with Q of 1 and Q prime of 0, and we're just keeping that state we're holding. Here I'm just showing in a picture what we just discussed. So Q, we started off as a 1, Q prime as a 0, and so we see I've labeled it in green, the 1 and the 0. Then I show that Q prime, that 0 going through the inverter and becoming a 1, the S of a 0 and the now 1 after the inversion go through the OR gate and become a 1. That 1 coming from the Q gets inverted, fed back to the lower OR gate, but it gets inverted first, so it becomes a 0, and the R of 0, and this now inverted 0, 0 or 0 gives 0. So just labeling all the states and realizing that all these numbers are happy to stay where they are holding. Now the RS flip-flop circuitry is symmetric, so it's not surprising then if the state where Q is 0 and Q prime were 1, that the inputs S equals 0 and R equals 0 holds that state as well. Let's just talk through it. So if Q prime were 1, then not Q prime would be a 0. That is fed up into the upper OR gate along with the S, which was a 0, and 0 ORed with 0 gives 0, keeping the Q input low. So now the Q output is low, or it was low before and is still low. Not Q then becomes a 1 when it is inverted, and that not Q, which is now a 1, is ORed with the R input, which is a 0, but one of the inputs is a 1, so the Q prime was a 1, comes out of the OR gate, and so it holds that state as well. Now let us look at the set operation. So when S is 1 and R is 0, that is supposed to set the state to force Q to be high and Q prime to be low. Let's imagine we were in the opposite state to distinguish it from a hold. So let's say we start off with Q equals 0 and Q prime equals 1. So Q prime was a 1, that lower output was a 1, but when we invert that, when we're feeding back and inverting it, that Q, not Q prime, inverted Q prime now becomes a 0. That 0 is ORed with S, but the S input is a 1, and so the output of that upper OR gate is a 1. That's forcing the Q output to change from low to high. So now we have a 1 for Q. So now that output being fed back around, not Q, now becomes a 0. that 0 is ORed with the R input, which is a 0. And so you have 0 ORed with 0, and the Q prime is now a 0. So we have changed the state, and now Q is 1 and Q prime is 0. And once it reaches that state, then it will be happy and it will stay there. So here we're just showing it again. The red 1 and 0 are the inputs. The S was 1, the R was 0, so we are setting. This is the input for a set. The green is where we started, the state at which we started with Q of 0 and Q prime of 1. But the blue is where we end up. So we started with Q prime of a green 1, and that 1 came around and got inverted to become the green 0. But that green 0 and that red 1 from the S went through the OR gate and became a 1. So now we've become a 1. So now we are blue. We've changed. And that Q of 1 gets fed down through the feedback mechanism, down through, it gets inverted and becomes the blue 1 just going into the lower OR gate. That 0 and the R of 0, 0 or 0 is 0, and now Q prime has changed to a 0, the blue 0. Once it's reached that stage, then it's happy. The blue, the green had to change to the blue, but the blue will be satisfied to stay where it is. We are now on the upper half ORing a 1 and a 1 and getting a 1, and on the lower half ORing a 0 and a 0 and it's becoming a 0, and it's happy in that state. It will stay there. As we've just argued, if S is 1 and R is 0 and Q is 1 and Q prime is 0, it's happy in that state. So if we had a 1 in the flip-flop and we go into the set state, it's just happy to remain in that state with Q1 and Q prime 0. Let's just go through the argument to be sure. Q prime was a 0, not Q prime is a 1. That 1 gets ORed with S, which is also a 1, 1 or 1. I'll give you a 1 for the Q output. The Q output is a 1. Inverting it, not Q, gives a 0. That 0 is inverted with the R, or 0 or 0 gives a 0, so the Q prime is a 0. So if whether we started in the opposite state, or whether we with Q0 and Q prime 1, or we started in the state with Q1 and Q prime of 0, if S is 1 and R is 0, we end up in the state where Q is 1. This is the set operation. Again, the circuit is symmetric, so it's not surprising that the input of S equals 0 and R equals 1 leads the lower, the Q prime output to be a 1 and the upper input Q to be a 0. But let's just be sure. So if Q started off at 0 and Q prime was 1, then we're going to take Q prime. Q prime was a 1. We invert it. That's a 0. That gets ORed with the S. For a reset, the S is 0. So we have 0 or 0 giving Q of 0. The Q output is 0. The inverting it gives us a 1. That 1 is ORed with the R, which is a 1, giving us a Q prime of 1. And so when S is 0 and R is 1, we are going to be forced into the state where Q is 0 and Q prime 1. So let's just finish our argument and start in the opposite state where Q was 1 and Q prime was 0. So we've been starting with Q prime, so let's start with Q prime. Q prime was 0, not Q prime will be 1. That 1 is ORed with an S, which is 0, but that gives us a 1 for the upper OR gate. And so the Q is at this stage is still a 1. Then that not Q was a 1 at this stage, so not Q becomes a 0. That 0 is ORed with the R, but the R input is a 1. So now Q prime gives a 1. Not Q prime, if Q prime is now a 1, not Q prime gives us a 0. That 0 is ORed with the S, which is also a 0, and 0 ORed with 0 gives 0. And so now the Q output has switched to 0. So we forced with S of 0 and R of 1. We forced Q to be 0. Once it's hit that stage, it's happy and will not change. The inputs S equals 1 and R equals 1 is what I call the undesired state, or the undesired input anyway. So we start with some state, some good state, Q equals 0 and Q prime equals 1. So then we take Q prime, which was 1, and we invert it, so that becomes a 0. That 0 is ORed with the S input, which is a 1, so that gives us an input for the Q of being a 1. That Q of 1 goes to the not Q and becomes a 0, but that 0 is ORed with an R, which is also a 1, giving Q prime output being a 1. So now we have Q and Q prime both 1s and both happy to be 1s. We have these, both outputs are equal, and we always want them to be opposite. So at this stage, this is an undesired state, so we're just not going to ever have that input. Now we're going to introduce a third input, which I'm calling clock, but which you might also call enable. And before S reaches the OR gate, I'm going to send it through an AND gate along with this new input called the clock. And the same thing for R. Before R reaches what we've established as the RS flip-flop going into the OR gate, it must go through the AND gate, and the other input to the AND gate is the clock. So the clock is being fed to both the S and the R inputs through AND gates before it reaches the old RS flip-flop. Now we've established previously that without the AND gates, the setting action occurred when S was 1 and R was 0. That was prior to the addition of the AND gates. Now with the addition of the AND gates and the new input clock, the output of the AND gate is what used to be the S input. And so when is that going to be high? When are we going to get the possibility of setting the flip-flop? Well, when S is high and the clock is high. And then similarly for the reset, we're only going to get the reset action when the clock is high and the reset is high. So we have our previous actions, but only when we only get the set when S is high and the clock is high. So this is giving us a little more control over when the setting or resetting, when the writing occurs. Next, we are going to achieve edge triggering by having one level clocked RS flip-flop feed into a second one, and the clocks will be inverted. One will be the opposite of the other. So what's sort of shaded in green there is our original RS flip-flop. You see that there are 2 of them, and then we've added the AND gates and a clock input, so we have a level controlled RS flip-flop, and the second flip-flop also has the AND gates so that it is level clocked, and then the clock input feeds into the first flip-flop, and then that clock input gets inverted before it reaches the second flip-flop. So this process of feeding the output of one clocked RS flip-flop into a second RS flip-flop with the opposite clock input leads to edge triggering. So let's start with the first flip-flop. So the first flip-flop is a level clocked flip-flop. So by the first one, I mean the one on the left. And so it is a standard level clocked flip-flop. And so when can we get setting or resetting? We can get those actions when the clock input is 1. When the clock is high, the first RS input can be set or reset, but the second RS flip-flop is getting the inverse of the clock, and so it is in the no change state. It is only when the clock goes to 0, and then that's when the first flip-flop goes into its no change. That's when the second flip-flop can be set or reset. So now that the clock is low, the second RS flip-flop, which is receiving the inverted clock, it can be set or reset, but it's being set or reset by the outputs of the first flip-flop. Its inputs are, its R and S inputs are the outputs of the first flip-flop, and the first flip-flop is in its no change state, so they are being held. So the inputs to the second flip-flop coming from the first flip-flop cannot change. So they might change initially when the clock first changed, but they cannot change subsequently because what's controlling them is the first flip-flop, which is in its no change state. So only when the clock changed do we see any possible setting or resetting. This is edge triggering, in this case, negative edge triggering.